Okay, welcome to the sixth class meeting of EC 202, Introduction to Probability and Random Processes. I have two announcements. First, the homework 3 is not due right now, due on this Wednesday, because our tutors decided to help you on Monday night, so I delayed that. However, from this week, every homework that will be usually due on Wednesday will cover up to the Mondays, nearest Mondays class meeting contents. Got it? And quiz number 1, as I announced in the PLMS, is fast coming. And you will have around 20 minutes only from immediately in the beginning of the corresponding class meeting. You may have around 5 minutes to solve all the true-false problems. So basically, you have to memorize all the true-false problems appeared in the homework. Possibly, the answer is reversed, so be careful. Do not just memorize, okay, if the problem starts with the event space, then it's true. Never do that, got it? And then you will have some numeric calculation problem that will take around 15 minutes. And probably you have around 5 more minutes to upload to the PLMS, but do not try to use this one to solve your problem, then there will be a disaster. Anyway, so in the last class meeting, we started to cover chapter 2 entitled Random Variables. Anybody remembers what is a random variable? It's not a variable. That is the most important thing. So the question, what is a random variable? The answer is definitely not a variable. What? But a function, okay? Random variable is now defined as a function. If random variable is a function, usually we assign a name. And in this textbook and almost every textbook and research papers, people use capitalized or uppercase letter X, Y, Z, blah, blah, blah. Got it? So this is the name of a random variable. Then the standard notation to specify a function or even generally a mapping rule is what? We put a set to clarify what is the domain of the function. What is the domain of a random variable? Then we put an arrow. This is read into, okay? Then we put another set that is called codomain. So if, as I claimed, a random variable is a function, what is the domain and what is the codomain? And if I refine the question, what is a real random variable or real valued random variable, then we clearly have R here. Be careful, codomain is not necessarily the same as all the set of all possible, all the outputs of the mapping node. It may contain the set of all outputs. So as we say, it is a real random variable. It's safe to put this set of all real numbers as the codomain. Got it? Then what about this one? In order to answer this question, we have to assume that there is a hidden or underlying probability space that models hidden random experiments. So we have a box that outputs an outcome S. And the mechanism of this box is mathematically described by these 3 things, so-called the sample space, a sigma algebra of subsets of the sample space, and the probability measure P. So here goes the mapping rule X, which means that S, the outcome, is the input to the function. And this one is what? A member of sample space. So here goes S. Got it? So now we have seen that a random variable is a function from the sample space of the underlying probability space into the set of real numbers or a real line. Got it? Of course, you may say that, well, professor, if I just roll a die and assuming that dots mean numbers, then this random experiment gives me what? A box that is random number generator. And we only have these 6 numbers. So do we really need this notion of a function? And even in this case, probably many of you may say that, I don't know about this one. What is this one? And there comes the confusion. And I also suffered a lot. However, last time I've shown you a Venn diagram. You remember? And I made an analogy to signal-gen systems. So what we are going to do is this one. Even though there are many random experiments, and intrinsically it generates numeric numbers as outcomes. However, we are not going to view individual random experiments that generates numeric numbers, but group them together and put all of them into this subset. So among all possible random variables, which means every possible random experiments that generates numeric real numbers, we are going to put a fence and saying that, hey, everybody come here, right? And then we are going to have very interesting new event space. That is this one. So what we are going to do is that all the random variables now have the same sample space, that is R, and the same sigma algebra, that is the Borel sigma algebra. And the only difference is what? The only difference that distinguishes each different distribution is what? Is the induced probability measure. Ready? And this induced probability measure admits a set because this is a collection of sets called Borel sets. Most representative Borel sets are intervals, like 1, 2, 5, something like that. However, there are many weird, crazy-shaped Borel sets. So let's say that a set B is a Borel set. Then in that case, the probability event that our X, the output, is a member of Borel set B is computed in this way. And you may again say that, what about the previous die rolling experiment? Still, we are going to use this one, but the key is that when we construct this induced probability space, we are going to put this kind of constraint. So except the possible outcomes of rolling die experiment, we assign 0 probability for every other things. So in this rolling die experiment, if you want to evaluate this probability of event, then that is 0. Of course, this is also 0 and so on. Got it? So in this way, we unify all possible random experiments that generate numeric numbers, real numeric numbers in this set. And we are now be able to develop a new theory. Got it? Anyway. So last time we've seen this block diagram. As I told you, we just assume that there exists an underlying hidden probability space. And here is a measurable function. Why we call this function measurable? Because we want to compute an inverse image so that we can directly use this probability measure in computing an event in terms of this x. Anyway, so as I told you, a random variable is now precisely defined as a real valued measurable function. However, we still want to use a very shorthand notations because it is very cumbersome to write all these curly brackets as in the sample space of the abstract underlying probability space and capital X of S, that is a function evaluated at S greater than or equal to 5. So in order to simplify this notation, we just write it this way. Or even sometimes we do not put the curly brackets. So be careful. That originally means this set, that is what? That is a member of the sigma algebra of the subsets of the sample space. Got it? Now here goes the induced probability space, which I already told you. The key idea is this one. Given the set of real numbers, we may construct a lot of sigma algebra. So for example, is this a sigma algebra? I told you it's not, okay? And then we may construct a lot of sigma algebra, but what is important is that we want to have a single very, very useful sigma algebra that is generated by very simple set. And Borel sigma algebra is interestingly generated by, again, this term is very major theoretic, but anyway, this type of intervals, which means that by applying countable set operations on possibly countably infinite number of half-infinite intervals, you may construct every Borel set in the Borel sigma algebra, and these Borel sets are all measurable. So this idea gives us an interesting function. So let's define a function capital F sub capital X of X, defined as the induced probability measure evaluated at this interval. So as I told you, given 1 and 2, 1 is the probability space of the underlying random experiment. and the random variable x. Actually, 1, 2 together is equivalent to this new triplet probability space having real set, the Borel sigma algebra, and the induced probability measure. And using this induced probability measure, we may define a function. And here comes surprising thing. Even though this function, capital F sub capital X over X, defined only for the induced probability measure evaluated on this form of the Borel set, actually they are perfectly equivalent. So if you know the induced probability measure, that is same as you know this one. It's kind of obvious by definition. The kind of converse is surprising. If you know this function, now we are going to call this as cumulative distribution function, simply CDF for all R. This is equivalent that you know the entire induced probability measure. So they are equivalent functions. Since they are equivalent, in many undergraduate textbooks, authors avoid even talking about induced probability measures. Some textbook talks about what? The underlying probability space and random variable as a function from the sample space to the set of all real numbers. But they rarely talk about induced probability measures, but just say that, okay, this is the theory, but now let's think about PDF, CDF, PMF, and something like that. There were missing link. And the missing link was the induced probability measure. And since they are equivalent, what? Do you want to talk about Borel sigma algebra to undergraduate students? Usually not. That's why most of the undergraduate textbooks, after they show these notations definition, they immediately move to CDF, the definition of cumulative distribution function. Got it? So now you know what is the story. One of the reasons why I talk about this one, even though most of the undergraduate books don't talk about that, is that, as I told you, this course is now converted to a 202, which means that it's more introductory course than computing something. So what I want to show you is that what is the fundamentals, even though we just read it and memorize as if we read some science, popular science books in our high school days. Many of you have read Carl Sagan's Cosmos or Stephen Hawking's History of Time. But most of the important parts in the books were actually research papers. You just enjoyed that without understanding every details behind the papers. And this course will be a little bit similar to that whenever I talk about major theoretic concepts or fundamentals. However, you may enjoy that because I'm not going to ask you to seriously prove anything. Got it? I believe this type of exposure to the major theoretic probability theory may help you, many of you, in the future, not right now. When you take more advanced courses, when you study more deeply in a specific subject. Right? So even though I do not cover the topics as if it is a mathematics course, please understand. Okay. Anyway, so this is the key. So CDF is more fundamental thing actually than PDF. Even though when I was a high school student, the probability density function and so-called probability mass function were taught first. And at that time, my teachers were not able to clearly explain why there is strange notion of CDF, why we integrate or sum up those probability density or mass functions and define it. It is because it's more fundamental, right? And the second one is that whenever we define something, I asked you to check what? The existence and uniqueness of what you just have defined, right? Interestingly, CDF, the cumulative distribution function, given a random variable, always exists. And it's, of course, unique. What does that mean? As I told you, you don't need to know the induced probability measure at all. Just the CDF contains all the information about the random variable. You don't need this abstract probability space and strange measurable function. This is everything for a random variable. By the way, here is some be alert type note. And there are some engineering problems. You want to assign, for example, plus infinity as the output of a random variable. For example, suppose you send an IP packet on the internet and you want to receive the acknowledgement. The problem is that your packet may got lost or your ACK packet may got lost during the routing. In that case, what kind of number do we have to assign? Infinity, because it didn't come back, right? The echo didn't come back. And that round trip time would be well modeled as a random variable. So definitely, due to the mechanism of the internet, we have to have assigned sometimes infinity. The problem of my definition and most of the undergraduate level random variables is that, as you see, what does that mean? Can you assign plus infinity here? No, because the set R contains all finite real numbers, which excludes, of course, plus minus infinity. So what happens if you really want to assign plus infinity or negative infinity, positive or negative infinity? You must be careful, okay? So I'm giving you a warning. One good thing is that in this course, that will never happen, okay? So that's okay. However, some of you may confront that kind of trouble in your future research. Got it? So remember that what you learned here excluded the plus minus infinity, so-called point mass at positive or negative infinity. However, at a very rare times, you need that. And at that time, try to find good resources explaining that kind of strange phenomena, and then apply after re-evaluating all your previous knowledges. Got it? Be careful. I warned you, right? This may appear as true-false problem, even though I will never ask you to solve some random variable having positive or negative infinity as a value. Anyway, by the way, I have just given you a very important observation. The CDF is equivalent to the induced probability measure, so it contains all the information about a random variable. Then you may guess next section would be titled as the CDF and its properties, but I'm not doing that because what I have found from many years of experience is that many of you or my former students, even though they performed well in the exams and quizzes and homework, I found that after only a few years, they have no idea about what is a random variable. I really got disappointed. So I devised kind of this section that is not in our standard textbooks. So this section introduces you so-called the strip plot and 1D scatter plot or dot plot and histogram, as you learned in statistics courses, and normalized histograms and its kind of limit as the bin size tends to 0. Why do I do that? Because the procedure I just told you is the most intuitive and most appealing to our vision. So let's see. Here goes National College Entrance Exam problem, 1991. Probably most of your parents, right, were younger than high school, 3rd grade at that time, right? Of course, I was the second year undergraduate student. And I remember this problem because my cousin was taking the exam, and at that time I was waiting outside the room and solve this problem. So the question is this. You know already the standard Gaussian with 0 mean unit variance. Now the question, this is math problem. You take 10 samples independently from that random variable and put dots on a straight line. Now, which one, 1, 2, 3, 4 among, looks most likely? Got it? So are you ready? So number 1, raise your hand. Answer is number 1. Okay. Number 2. Okay. Number 3. Number 4. I didn't exactly copy the problem, but the answer was more like this one. Okay. But most of the students who lost the point to selected something like this, but I believe that this has so much dispersion, so you would not answer in that way. By the way, what is this one? This is called a strip plot or one-dimensional scatter plot. So you put dots whenever you put a dot whenever you have observation, right? So you may use this idea to visualize what kind of behavior a random variable has. And something similar is so-called dot plot. And that is not much used in mathematics or engineering, but interestingly, that is heavily used in economics, like this one. This is so-called FOMC dot plot. Probably some of you who are interested in investing in stocks may know this one. 연방준비제도 이사회 점도표. This is translated as 점도표 dot plot. And what is this one? So it's like this. This is kind of prediction. Suppose that this is year 2023. And we ask the members of this board of governors, there are many, and what do you expect about, for example, federal fund rate, 이자율, for example, and this number of dots corresponds to how many people in the board guessed that would be a proper number. Then you see that for year 2024, 5 members, right, expected around 4.5, and 4.25, 4.75, something like that. This is so-called FOMC dot plot, FOMC 점도표 in Korea. So it's somewhat not appealing to engineers because, as you see here, this dots physically has size, areas, right? So if many people put dots to the same number, then it's hard to count, which means that hard to understand how many actually kind of put dots there. So it's not good. And many of you will say that that is the same as general strip plot. You are right. And what is the worst case? In this problem, we consider a Gaussian random variable, normal random variable. So it's highly unlikely that just a few dots will overlap. However, what about you roll an unfair die? What will happen? Or even you roll a fair die, what happens? So the possible numbers are only 6, right? And whenever you roll a die, 1, 3, 2, 6, 1, oops, right? That's why actually dot plot 점도표 allows you to put this way or even that way, okay? You can stack upwards if that really horizontally putting dots misleading. Got it? So anyway, there are many heuristic ways. However, almost everyone has its flaw. But people try to standardize visualization methods because anyway, visualizing is really visually appealing. That's why people devise the idea of histogram. And you all believe that you know what is histogram. But actually, you are not. That's the problem. So suppose you are using MATLAB to visualize some data. For example, whenever I give you final grades, what do? I usually use MATLAB, not Excel. I'm still MATLAB guy. MATLAB and plot the histogram of your final score. And take a look at it. Okay, where do I put a bar to divide A and B, something like that. Sometimes I have a very clear cut. Sometimes not. In that case, the first thing I do is that choose different bin size. In that case, I have good separation, right? So bin size looks very important. The problem is that MATLAB long ago had a strange function called hist. And now it has histogram. And as a early adopter of MATLAB, because I used it from my graduate study, 1995, 30 years ago. At that time, MATLAB had hist. So I used it for a long time. The problem of hist is that it does not follow international standard. It has no idea about bin. It just accepts two things. And the first one is the data vector. And second one is kind of strange thing, centroid of each bin. What does that mean? I may non-uniformly put bin sizes. And since every vectors are finite, what happens to the rightmost bin and leftmost bin? And in this case, if my number data goes outside the second last and second last bin, they put the data to the first or last bins. So no data is missing. That is good for old misleading hist. But histogram, this is very strange thing. And I almost made serious mistake when I just replaced my old MATLAB code with hist, just replacing all hist to histogram. Because histogram admits the data and bins defined each number defines the end point of each bin. So here I told you center point. And this is end point. And you may say that they are almost the same, but they are not. Histogram, this function, and the standard definition of histogram with given bin endpoints is very strange. If data goes outside that bin, it's ignored. So your input data is hundreds samples. When you draw histogram, only 80 could appear. Because 10 greater than your biggest bin and 10, for example, smaller than the smallest bin is ignored. So be careful. Got it? I warned you. I warned you. Yeah, so in Korean 당해봐야 알죠, 그렇죠? 예, 이것 때문에 뭐 이상한 일을 당해보면 알게 돼요. 예, 제가 경고했어요, 분명히. 여러분들 아주 큰 문제 봉착할 수 있어요, 언젠가. Okay, let me go back to English. So read this one. Got it? If you really want to use histogram in your engineering plotting, you must be, okay, Professor Cho warned me. Let me look the definition carefully. Interesting thing is this one. When you are given endpoints of a bin, left inclusive, right exclusive, except the rightmost one. The rightmost one, the biggest bin, both sides, both numbers inclusive. And as I told you, if your data C is greater than B, this data is ignored. If suppose this is the leftmost bin and your data C is less than A, that is ignored by definition of histogram. Got it? Anyway, so using histogram, not hist, got it? You may draw bell curve. For example, rand n, the MATLAB command, gives you random normal number, random Gaussian number. This means that you generate 10,000 independent generation of Gaussian random variable. Okay? And we use histogram. And as you see that only the data is going in. In that case, MATLAB automatically selects the bin edges. And it returns number of bins, values, and some other things. Also, when you use MATLAB, you can normalize. And you may put some options like PDF. So maybe this homework will give you some coding homework. Use MATLAB, plot histogram after generating 10,000 Gaussian random variables with bin edge points, blah, blah, blah. Got it? And some of you may say that I never learned how to use MATLAB. Then learn it. Got it? It's not that difficult. Some of you may say that I don't have the software. Good news is that the Postec has license, so you can download it. Or you may say that my computer is too disk hungry, MATLAB is too big. We have online account. So as far as you are a Postec student, then you can join MathWorks homepage and you can access MATLAB through the internet without installing it on your computer. Got it? So there will be a homework problem. Anyway, HIST is not recommended. It's never use it. But it has some good thing because it never drops out your data. Anyway, normalization is very important. So why? Suppose you use just a histogram to plot many independently generated Gaussian numbers. What will happen? If you generate 10,000, if you generate 100,000, what happens? If you fix your bin, then this height goes up, right? That's why we love normalization. Normalized histogram means that the area, in Korean, 면적, the sum of area is normalized to 1, some unit. Got it? So if you sum up the area of each rectangle, then you have 1. It looks very similar to what you already learned, PDF, probability density function you learned in high school. And if you just leave the bin size fixed, then you will have some function like this, right? We don't love that. So what we do is that as we increase the number of samples, we also reduce the biggest size of each bin, biggest size of the bins. In that case, we may have something very smooth for this bell curve, right? And that is exactly the idea of probability density function. Even though I will say that, hey, actually, probability density function is the derivative of the CDF. And many textbooks just says PDF is the derivative of CDF. Of course, that is one of the mathematical definition. However, it has very appealing intuition behind it. We start from, for example, strip plot or dot plot. That's not that good. We move to histogram. We normalize somehow. We make the bin size tends to 0. And then we have something smooth, for example, for the continuous random variable, so-called. Then what about that rolling die experiment? What do you guess? What will happen if you apply this idea of normalized histogram and its limit? You will see something very strange, right? As you reduce the bin size, you have what? You have these rectangles with very small width and very high height, right? And by the definition of the normalized histogram, what would be the sum of these sizes, the areas of these rectangles? It's 1. And that may sound something familiar to what you learned in signal-gen systems. Actually, each rectangle kind of converges to delta functions located at 1, 2, 3, 4, 5, and 6. And if our die is a fair die, the limit would be what? Even though height tends to infinity, their heights would be almost the same. And the area of each rectangle would be approximately 1/6. Got it? So that's really almost the same as what you have in your mind as the definition of delta function. This shows why sometimes if we differentiate a CDF to obtain PDF, we have delta functions. Got it? So the trouble is that some of you have no idea what is a direct delta function. Okay, that's not good. If you are currently taking signal-gen systems together, then that will appear soon or already appeared in your signal-gen systems course. And just think in this way. Direct delta function actually is not a function, but with infinitesimally small width and infinitely large height. And its integration gives you 1. And this is denoted by delta of x if the horizontal axis means x. Now, if you have delta of x minus 5, what does that mean? You have 5 and some very high function. Usually, we put double arrow here and write 1 in order to distinguish this function with area 1 with, for example, 2 times delta x of 6 with area size 2. Got it? So this is not a good precise way to visualize, but that is the convention. Anyway, since if the outcomes of our numeric the numeric numbers of our random experiment is real, but our sample space, not the entire real number of the induced probability space, but just the sample space of the random experiment, simply modeled, is discrete set, then you have no way to avoid using delta function. And that is not really appealing. That's why we have another function, probability mass function. And the mass function is somewhat strange. See that? This is so-called empirical 경험적인. So you roll the die a lot of times. So you have empirical PDF that has delta function in the limit. But here is more appealing thing for the discrete case. So you just put lines, okay, with height, for example, 1/6 when you have a fair die, and you may call this is a function. Of course, this is a function. And usually we use lowercase x, subscript lowercase x with uppercase x. So this is lowercase p. Okay, let me do this as you learned in English course. So p lowercase subscript x capitalized of x. Got it? So lower, upper, lower. And this function, p sub x, may be a function from R into 0 to 1. And in this case, px1 equals 1/6, and px2, 3/6 is 1/6. And for all the other real numbers, it's 0. It's a legitimate function, right? And this function, the problem is that you cannot integrate to get 1. You just need to sum up, okay? That's the difference. This type of function is more appealing in visualization, and it is called probability mass function. You have a mass, 질량, point mass or probability mass at this point with that height. Got it? Anyway, so you just have seen kind of idea development. Theoretically, as I told you, CDF is fundamental because it's equivalent to the induced probability measure. However, histogram and its limit, the PDF, is more appealing to our intuition. Of course, mathematically precisely, they are linked by what? Differentiation and integration. If you differentiate CDF, you get PDF. Got it? Now, here goes another problem I myself made. I don't remember which year it appeared, but at that time, in order to enter our MS program, our department, you had to have oral test. So you come to some of professor's office, and you have 20 minutes to solve 3 problems, something like that. This is one of the problems. So let's solve it. given a continuous random variable, Gaussian. You know what is this, right? And you have a function, g, and here goes 3 problems. Actually, only this one was given in the first year. Amazingly, there were too many wrong answers. So probably a few years later, I put more sub problems. So let's try to solve it. Draw a block diagram of this random real number generator. So you have here n, 0, 1. Here goes x. And here goes g. And here goes y. You see, right? Y is named this way. So you have just generated a random variable y by using random variable x. Or in other words, you have a random number generator that generates x, but you have a new system that generates random variable y. The question is, when x is Gaussian normal and g is this function shown here, right? What is the output probability distribution actually at that time as the PDF, probability density function of output? And there were many strange answers. The first one was this one, of course. Same. Second one was, I really got shocked. This one. And some other things. No correct answer. So, anybody? Number 1 is your answer. Number 2? Number 3? There's no number 3 here. So, how can you solve this problem without having any knowledge about this course, but have the intuition? Histogram. Okay? So let's start from here. So you generate X, and you know that college entrance exam thing, right? If you ask box to the generator box to generate X, then it will give you something, some points, dots, closer to 0 most of times, but sometimes very large, right? That numbers are generated. Now, it's mapped by this function. What happens? Whenever input is positive number, it assigns 1. Whenever its input is negative number, it assigns negative 1. Then, what is the possible output of this block? Either 1 or negative 1. So if you plot a dot plot, it's like you just put dots at positive and negative infinity. Now let's convert it to a histogram, normalize histogram, and consider the limit of it by generating many x and reducing the bin size smaller and smaller. What will happen? You will have 2 delta functions, one located here and the other located there. And what would be the height of them? 1/2. So you have 1/2 delta y plus 1 and 1/2 delta y minus 1. That's the answer. Amazingly, many students answered this way, just multiplying these 2 figures. Got it? Amazing. I got really shocked. And I believe if you forget about my approach of using histogram, dot plots, and normalized histogram is limit, you will make the same mistake in a few years. Okay, you don't believe you will, but I'm sure many of you will answer this way. Number 2, I know that. So remember my advice. Use your brain. Use the histogram, dot plot, or strip plot. Got it? Then you will never miss anything. Now, even though I emphasize this way, there goes another problem. So several years earlier, or 2 years earlier than that college entrance exam year, 1989. It was a miserable year to my life because I was redoing my high school third year in 종로 Academy. 종로학원을 다니고 있었어요. 재수생, 소위 말해서. So at that time, it was really miserable. It's like this. I just failed to enter the university. But if I take tomorrow, I'm almost sure that I can pass. But I had to wait 1 year. Can you imagine that frustration? So what usually my friend did at 종로 Academy was that they enjoyed a lot of challenging problems. And also the academy provided that kind of problem. So it's like at that time, the math subject was maximum 75. And when I was high school, third year high school year, mostly my score was 71 to 75. But 종로 Academy provided very difficult problems. So suddenly my score dropped to 51 to 55. I lost more than 10 problems. And here goes one very similar problem. So there are two friends coming to a promised place at random times within plus minus minutes from the promised time. And they will wait exactly 2 minutes for each other. What is the probability that they meet? Got it? Anybody who can solve this one? At that time, when I saw this problem, I just froze. I could not solve. I could not solve by using any high school probability random variable knowledge to solve this one. But amazing thing happened. The next guy, yeah, he's still my friend, and I met him around 1 month ago. Still friend, and we joined the same amateur astronomy club, and still we meet. And this guy just solved it after sketching something. I really got shocked. And here goes his idea. So when he was the only guy among around hundreds of us, in 종로 Academy, there were around hundreds seats given a classroom. 1 out of 100. And he just said that, okay, let me think in 2 dimensions. And let's suppose this is the origin is the promised time. And this X is one person and Y is the other person's arriving time. And he said, X arrives plus minus 5 minutes from the promised time. And Y arrives plus minus 5 minutes. What does that mean? Here goes the shocking part. He really put dots there. Got it? For example, what does this mean? X guy arrived 5 minutes later than the promised time, and Y guy or girl arrived at 2 minutes behind after the promised one. So he said that if they are independent, at that time he didn't explain what the independent mean, but just he said that there would be a lot of dots uniformly scattered within this square. And he said that they wait 2 minutes. What does that mean? X minus Y, absolute valued, is less than 2. Then they meet. And you know how to plot this one as a 종로 Academy student, right? It's very simple. And he computed the entire area, right, in the denominator, and that strip area in the numerator and solved it. Do you understand what he did? He really used scatter plot to get the idea and solve the problem. At that time, when I was 18 years old, I couldn't do that. I just could one-dimensional thing. But he immediately extended that idea to two-dimension. At that time, I realized that this guy is not a normal guy. But we had the question like, so he's so extraordinary. Why he is here, right? If he's so extraordinary, he should have entered the university without failing. That was very interesting question we had at that time. But anyway, so it was like a high school or science high school these days. Anyway, do you understand what I mean? So this shows the importance of what? Visualization, especially using scatter plots. This is two-dimensional scatter plot. And actually, we are going back to this problem after a few chapters. Got it? Yeah, see this beautiful dot plot? Anyway, so here goes the formal 2.3 section. So it's about cumulative distribution function. And its definition is very, very simple. It is defined what? This way. CDF of a random variable x, usually denoted by capital F subscript capital X, right? This means, hey, I'm the CDF of random variable x. And this is the argument of the function. And what is this? Defined as probability of the event that capital X less than or equal to X. What does that mean? In terms of the induced probability measure, capital P sub capital X is the probability of the Borel set negative infinity to X. In terms of the probability measure, we have to write this way. Right? Got it? But anyway, so this is the CDF. And as I told you, it exists and unique, and it's equivalent to the induced probability measure, which means that it characterizes the random variable. What does that mean by characterize? Fully describe. Okay? So full description is very, very important because it's different from partial description. As you remember, you know what is the mean and variance of a random variable already, right? There are many different random variables having the same pair of mean and variance, right? So mean and variance may not fully describe a random variable. However, probability distribution, especially CDF, uniquely describes and always fully describes a random variable. By the way, it's kind of not inverse, but the inequality flipped is called the CCDF, complementary CDF, and it's also very important. And we will go back to the figures. And if we do not allow plus minus infinity, then here we do not allow, then we have a very interesting property of CDF. For example, CDF evaluated at smaller and smaller value, it goes to 0. So it's like you go that direction. The CDF value diminishes to 0. Reversely, if you evaluate bigger and bigger x, then its value becomes closer and closer to 1. If you have that one, not R bar, which includes plus minus infinity, not this one, okay? And also, CDF is defined as probability, so its height can never go up 1, never below 0. Got it? And what about this one? This is monotone increasing property. Why? Because the interval negative infinity 5 and interval negative infinity 6. This one is included here, right? And you know from the axiom of probability that this holds if A is a subset of B. Same thing, okay? And if you want to compute the interval from x1 to x2, be careful. This one does not have equality. Then you can write this way. And why this is so? Because your interval x1, x2 equals negative infinity x1 complement intersected with negative infinity x2. Got it? So that's why you have this. Anyway, the sixth property is very interesting and called right continuity. Why this is asked it this way? Because CDF may be discontinuous sometimes. Something like this. It may increase, but here we may have jump. But if you, so at some x0, we have a jump in CDF of some random variable y. But if you move downwards to y0, then your value becomes smaller. And here you have some value that is same as your limit. So if you approach from the right, then you have continuity. So continuity means that you can change the order between limit and function, right? So if you approach from the right, then you can switch the order of limit and function operation. That is the property of CDF. And why this holds? Because we defined it this way. Here we include X. By the way, if you read very, very, very old textbooks around 1930s, well, probably Postec does not have the book, but when I was a graduate student, I could find some very old book, and they have negative x2, negative infinity to x excluding x. Actually, that can construct a new theory with little bit difference. It's perfectly okay. But most of people kind of has decided to use the right continuous CDF. It's like Gulliver's Travel. Probably you remember that Dwarf's Land. They fight over how to break the egg, right? Yeah, and everybody moved conformed to one standard. Fortunately, now already you know the terminology. 이산 확률 변수, discrete random variable, and 연속 확률 변수, continuous random variable, and you have the idea. But actually, that terminology is based on the CDF. So we take a look at the CDF, and if we find the CDF is a continuous function without any discontinuity, then we call the random variable a continuous random variable. Got it? There are many continuous random variables, right? And if we have piecewise constant function with jump discontinuities, then we call it's a discrete random variable. Of course, CDF may look like that, as I just have shown you, right? In that case, interestingly, we can always construct this type of piecewise constant with jump discontinuities as a weighted sum of a continuous CDF and discrete CDF. So we have three classifications, three classes of random variables. One is discrete, the other is continuous, and the third is mixed. And mixed random variable has CDF. that is really in this way. So it's a mixture. P is a number between 0 and 1. And here, this would be a discrete random variable CDF. And this is a continuous random variable CDF. That is, this is the weighted sum of two CDFs, continuous and discrete. And your question would be, is there any other form? Yes, but we are not handling that because that just exists mathematically. But in engineering problems, we are enough. We are happy with 3 class of random variables. Got it? Be careful. Mixed random variables are very, very important. Sometimes we mix 2 continuous random variables, 3 continuous random variables, 5 continuous random variables, sometimes. So when you mix continuous random variables, of course you have a continuous random variable. What I'm saying is that a mixed random variable, here mixed means it is a random variable, it is mixed. That does not mean. Mixed random variable means that it's kind of a part discrete, a part continuous. Be careful, got it? So this mixed means, mixed may mean a terminology we use in this classification or a normal adjective just. So you mix 2 random variables sometimes. So be careful. Anyway, so CDF is very useful. And here goes the PDF. By definition, PDF is defined as the derivative of CDF. And mathematically speaking, whenever you have discontinuity, then you cannot differentiate. One good thing with electrical engineers is that whenever you have jump discontinuity in the CDF, you may put a delta function there. So for example, suppose you have some continuous function, but here you have jump discontinuity in the CDF. And this height of jump is 0.5. Then, as I told you, this may be the sum of that one and sum of this one. Oh, sorry about that. Not this one. Not yet. So if you add these 2 functions up, what will happen? You have the upper one, right? So if you differentiate, suppose that continuous one is differentiable, then this is just differentiated. And what do you have? Whenever you have jump discontinuity, you may write it this way: u of x minus x0, 0.5. So this is the unit step function you learned, I hope, in your signal gen systems. So let me define. X of u is either 0 or 1. Okay, I'd better write this way. U of x is the indicator function of x. What does that mean? If x is greater than or equal to 0, it's 1. It's less than 0, it's 0, right? You know what is an indicator function. We've already covered this one. So if you differentiate this one in electrical engineering, what do we have? Delta of x. Got it? So if we introduce delta functions in describing PDFs, we are free. We don't need to even think about much of CDF. So PDF is very, very appealing, as I told you, from the dot scatter plot or histogram, normalized histogram. And it's also very appealing to electrical engineers who are familiar with handling delta functions. Anyway, this density function, mathematically speaking, does not always exist. However, we may make it pseudo exist by introducing delta functions. The problem is that from the fundamental theorem of calculus, its integration must be the same as CDF. The trouble is that when you have a function, two functions, suppose we have exactly same two functions except this point. They are different functions, right? Because they differ at x0. However, if you integrate this one to get CDF, actually, they are same because you only replace a single point. What does that mean? PDF may not be unique. PDF may not be uniquely determined because you can change the PDF value if, especially when the random variable is a continuous random variable without modifying your CDF. Okay. Anyway, so PDF is a little bit inferior in precisely handling our ideas. That's why mathematicians or even electrical engineers love using CDF. The problem is that probably you remember expected value. And this may contain delta function or something. So instead of using this one, people use CDF. What is this one, by the way? This is so-called Stilcher's integral. And some of you know that, right? This is general Riemann or Lebesgue integral, but this is Riemann-Stilcher's or Lebesgue-Stilcher's integral. And I really hated that one when I first saw it. So you will see this expression again and again. But I'm not going to seriously ask you to do some Stilcher's integration. But you have to know it. Got it? As an engineer, this is kind of common sense. Anyway, so let me see. I believe I covered, yeah, up to this point. Yeah. So that's all for today, and see you this Wednesday.